The human need to explore is deep within all of us. Our ancestors crossed mountain ranges, sailed archipelagos, and sought out the unexpected while always looking to the stars. We are curious, and now we are at a place where we can pioneer new horizons. Because Earth, this blue planet, in all its beauty, is just our starting point.
When did scientists come to know that space is empty and a vacuum? That pale blue dot is us, Earth from 1.44 billion kilometers away. Space is not a perfect vacuum, but a partial vacuum. That means that there is still some matter floating around. Even in the most remote regions of the cosmos, the ancient Greeks were among the first to speculate about the existence of a vacuum. Some of them, like Aristotle and Plato, argued that a vacuum was impossible, because nature abhors a void. They believed that everything was made of four elements: earth, water, air, and fire, and these elements filled up all the space in the universe. Other Greek philosophers, like Democritus and Epicurus, disagreed. They proposed that everything was made of tiny indivisible particles called atoms, and that there was empty space between them. They also suggested that there could be empty space beyond the edge of the world, where nothing existed. The debate about the vacuum continued for centuries, until the 17th century, when scientists started to perform experiments with air pumps and barometers. They showed that air had weight and pressure, and that it could be removed from a sealed container. This proved that a vacuum was possible, at least on Earth. But what about outer space? Was it also a vacuum? The first clue came from Galileo Galilei, who observed the phases of Venus with his telescope in 1610. He realized that Venus orbited around the Sun, not the Earth, as the geocentric model suggested. This implied that there was a huge gap between the Earth and Venus, where nothing could be seen. Later, in 1672, Isaac Newton used his newly invented reflecting telescope to observe the Moon. He noticed that the Moon had mountains and craters, just like the Earth. He also calculated that the Moon's gravity was much weaker than the Earth's. He concluded that there was no atmosphere on the Moon, and that it was surrounded by empty space. Newton thought space was perfectly empty, because he needed this assumption for his theory of gravity. He believed that gravity was a force that acted instantaneously across any distance, and that it would be hindered by any medium in between. However, Newton's idea of a perfect vacuum was challenged by other scientists who proposed different theories of light and electromagnetism. They argued that light was a wave that needed a medium to propagate through space. They called this medium the ether, or the luminiferous ether. They imagined it as a very thin and elastic substance that filled all of space. The existence of the ether was put to the test in 1887 by Albert Michelson and Edward Morley. They designed an experiment to measure the speed of light in different directions, expecting to find a difference due to the motion of the Earth through the ether. They found no difference at all. Their results suggested that either the ether did not exist or it had no effect on light. The final blow to the ether came from Albert Einstein's theory of relativity in 1905. Einstein showed that light was both a wave and a particle, a photon, and that it did not need any medium to travel through space. He also showed that gravity was not a force but a consequence of the curvature of spacetime, caused by mass and energy. Einstein's theory revolutionized our understanding of space and time. It also confirmed that space was mostly empty and free of any ether or other substance. But it also opened up new possibilities for what could exist in space. According to quantum physics, which emerged in the early 20th century, even vacuums are not completely empty. They are filled with quantum fluctuations, random and temporary changes in energy and matter that pop in and out of existence. These fluctuations can create virtual particles, pairs of particles and antiparticles that annihilate each other as soon as they appear. These virtual particles are not directly observable, but they have indirect effects on real particles and fields. For example, They can affect the mass and charge of electrons, the Lamb shift, or create a tiny force between two metal plates in a vacuum, the Casimir effect. Quantum fluctuations can also have dramatic consequences in extreme situations, such as near black holes or in the early universe. They can create real particles from the intense gravitational fields or the rapid expansion of space. They can also generate tiny ripples in spacetime called gravitational waves, which we have recently detected with advanced instruments. So, space is not a perfect vacuum, but a partial vacuum. It is mostly empty, but not completely empty. It contains some matter and radiation, as well as quantum fluctuations and virtual particles. And it can also create new forms of matter and energy under certain conditions.